Good evening, everybody. I have the distinct honor of welcoming everybody here this evening. Thank you so much for attending what I hope to be a very exciting evening. We have a very distinguished guest here this evening, who I'll introduce in just a moment, but first I'll introduce myself. My name is Dr. Kim Tate. I'm a senior curator here at the ROM in the mineralogy section, so I take care of all the minerals, meteorites, rocks, and gemstones here at the museum. So if you want to wear a tiara or hold a piece of the moon, you'd have to come talk to me. So make friends with me after the presentation if you like. I also am the lead curator of the exhibition here called The Nature in Brilliant Color. Hopefully many of you have already attended, and if you have not, I strongly recommend that you do. It's a wonderful exhibition, a little bit of a departure from the other exhibition that's going on right now. And what we tried to do, it's an exhibition that came from the Field Museum, but we tried to insert some ROM into the exhibition by adding some beautiful taxidermic specimens, as well as added a people and color section to the end as a nod to our art and culture collections that we have here at the museum, and as well as expanded some of the Canadian content. So you'll see an Arctic scenery that we added, as well as a blue jay, as people would expect here in Toronto. So yeah, I do hope that everybody has an opportunity to go see the exhibition. It was a labor of love, I can say. We worked really hard on that, and there's quite a lot of beautiful minerals for you to see. So, besides that, we have a very special guest here this evening. Dr. Robert Hazen is a senior staff scientist at the Carnegie Institute in Washington, D.C. He's also a professor of earth sciences at George Mason University. He did his bachelor's and his master's degree in geology at MIT and his PhD at Harvard University, and was also a NATO postdoctoral fellow at Cambridge University. So has quite a lot of excellent lineage, of course. He's an author of over 400 peer-reviewed articles and also 25 books on not only science, but also history and music. So very busy gentleman. He also has a mineral named after him. I do not have one yet. I'm very jealous. So Hazenite is the mineral name that was named in his honor. And there's only just 6,000 minerals, so you think of what an honor that is for somebody to name a mineral after you. His research is vast. I can say that. I've been reading his manuscripts since I was a very young mineralogist. His most recent work is talking about mineral origins and the focus between minerals and the biomolecules, and sort of these origins of minerals has been a really interesting focus that he's had. Since 2008, his colleagues and himself explored mineral evolution, and hopefully this is something that you've heard about in your studies, and if not, I expect you to Google it after this. And it really does a great job of using mineral data that exists out there and mining the information to make new and interesting discoveries. And I'm sure that he will talk a little bit about his work in his talk this evening. He was named principal investigator in 2008 of the Deep Carbon Observatory, and this was a significant group that was funded by the Alfred P. Sloan Foundation. There was over 1,000 collaborators, including myself, and 45 countries were involved in this. They had government, corporate, private sources. Almost $1 billion was put towards this effort, if you can imagine. In 2016, if you can imagine, he was a professional trumpeter, and also he retired after 40 years of doing this. And he performed numerous occasions at the Metropolitan, Boston, Washington Operas, Boston Symphony, National Symphony. So you can talk about that later, but he has very accomplished in many areas. My PhD supervisor, his name is Robert Downs. He is quite a famous mineralogist, and it turns out that Bob Downs' supervisor was our speaker this evening, Bob Hazen. And so my PhD advisor always talked about mineral heritage and mineral lineage. So in fact, I call him my academic grandfather in ways, and I did clear this with him before I can call him that. So without further ado, I'd like to introduce you to my grandfather, academics, Dr. Bob Hazen.
Oh, Kim, thank you for that gracious introduction. No grandfather could be more proud of his scientific granddaughter than I am of Kim Tate. It's such an honor and pleasure to be here at the ROM, this great museum, to talk about our remarkably beautiful planet. And when viewed from the moon, what we observe is this gorgeous blue planet with swirling white clouds, glimpses of brown and green continents, and we get a sense of the colors of our planet. We also get a sense that Earth is a planet of change. And part of that change has to do with the way minerals have formed. When we look at Earth history, we think about a timeline, and I want to take you through this quickly because I'll be using some of these terms. If you go back to the beginning, 4.567 billion years ago when Earth first formed, and we come forward in time, 3 billion, 2 billion, 2,500, where some very interesting things happen to minerals, and going forward all the way to the modern time. All the things we think of when we talk about life forms really are in this last little bit here. And if you go to the paleobiology displays here, you'll see many of the classic specimens from Canada that have informed us and then told us how our planet has changed through time. But I'm going to be doing this from the point of view of minerals. Minerals are astonishingly beautiful. They're varied, and it turns out they have a history. Thousands of colorful minerals are found on Earth and nowhere else in the solar system. And why is that? Let's take that journey together. Why is Earth unique in its mineral diversity? Well, first, let's just talk about why minerals are so important, why we study them. First, they're critically important to all the raw materials that we use in industry, manufacturing, critical to agriculture and the formation of soils. Minerals have been drivers of scientific discovery. Many Nobel Prizes have been won for physics and chemistry studies of minerals. They're also our key to understanding other planets and moons. When we go to Mars, when we go to other worlds, we need to know the mineralogy of those planets and moons because that tells us what's going on in the history. And of course, they're just astonishingly beautiful objects. So let's take a journey through time. The importance of mineralogy, when you think about the oldest thing that you can hold in your hand are certain very ancient rocks, meteorites, some of them more than 4.5 billion years old, nothing older that you can hold in your hand. They tell the stories of the origins, the evolution of planets and moons. And every single mineral specimen, when you go to the gorgeous displays here at this museum, every specimen has a history, it has a story, and it's information rich. It's a time capsule waiting to be opened. And so in 2008, as Kim mentioned, I introduced a field called mineral evolution. Seems like a strange concept. Do minerals really evolve? Well, the suites of minerals do. And what we look at in mineral evolution is the changing diversity and distribution of minerals as a consequence of new physical, chemical, and ultimately biological activities on our planet. Now, I'm going to use a term of art in mineralogy called a mineral species. And the International Mineralogical Association, that's the IMA, has protocols for approving new species. First of all, it has to be a naturally occurring solid. It has to have an idealized chemical composition like this quartz crystal, which is SiO2. And it has to have an idealized structure, the quartz structure. So every unique combination of a chemical composition and a structure is a mineral species, and there are about 6,000 approved species on Earth as of today. So in mineral evolution, we study several things. We look at the diversity of mineral species. We look at their distribution and the relative abundance through time. We think about things like their compositional ranges, and this is not just the major ideal elements, but the trace and minor elements that's present in every single mineral. And we look at the sizes and the shapes, the things you admire when you go to a museum. That's all part of the mineral evolution story, not part of the IMA classification, but it's part of the way we think about minerals and the stories they tell. We focus on the upper 3 kilometers of Earth's crust, because this is the part of mineralogy that's most accessible to study on our planet. It's what we're likely to find when we go to other planets and moons. And it's also where there's direct interaction with biology, which turns out to be critically important. Now, mineral evolution, the key idea is that minerals form through a combination of chemical, physical, and ultimately biological processes. And all these diverse minerals form in that way. And mineral evolution spans 4.5 billion years of Earth history. So we can think about mineral evolution in a series of stages, a timeline, if you will, each stage building on what came before. So let's look at that timeline. I sort of talk about the 0th stage because there were minerals that formed long before Earth. And these minerals are literally stardust. When you have a star that gets very old, it starts building up in its atmosphere carbon and silicon, oxygen, magnesium, and other elements that as the gaseous atmosphere of a star expands, it cools, and you start getting crystallization of about 25 different mineral types. But these aren't the kinds of minerals you're familiar with. They're all tiny, tiny things, a micron or a nanometer across. And nevertheless, that dust, that gas, would be the seed of planets. And so the question of mineral evolution is, how do you go? These are the dozen or so elements that are critical to those minerals. So how do you go from the starting point of every solar system in the cosmos, which is roughly 25 minerals formed of maybe up to 16 different essential elements, to what we see on Earth today? 6,000 different minerals with 72 different essential mineral-forming elements. So here's a timeline of 10 stages of mineral evolution, and let's look through this real quickly. This is a very qualitative way of describing mineral evolution, and it's what we first proposed in 2008, these 10 stages. So the first stage is what happens when the sun starts forming in the early nebula. It collapses hydrogen and helium primarily. The sun begins to burn. And as it does so, radiant energy sweeps out and starts melting clumps of dust into tiny droplets called chondrules. And then as those droplets cool, they form about 100 different new minerals, the very first minerals of our solar system. Those chondrules then come together to form all the different kinds of meteorites that fall to Earth today. Chondrules get into larger gravitational clumps. They may be a mile across, and then 10 miles across, and then 100 miles across. And when you get that large, there's enough internal heat to melt them. So the iron and nickel metal goes to the core to form iron. The core then can break apart and form the iron meteorites in our collections. And the outer part is a silicate mantle, and that has additional new minerals. And then you have alteration by water, you have alteration by heat, and other alteration by impacts, giving you about the 300 known minerals in meteorites today. So this is before Earth ever forms. Now, in the earliest stages of forming planet Earth, we think they're only about those 300 minerals if you have a dry world. So our moon, maybe 300 minerals is the max. Same thing for Mercury, that very hot, dry planet close to the sun. But Earth has a different set of tricks. Earth has a watery ocean. And so that water interacts with rocks, and you have all kinds of new minerals, things like hydroxides, clay minerals, ices that form at the pole. So these are minerals that occur on Earth that wouldn't occur on those dry worlds. And we think this probably is where Mars is today, about 450 different kinds of minerals which make up the planet, and Mars is sort of like a frozen version of Earth very early in its history. At least that's one hypothesis. Earth is larger, so it has other tricks up its sleeve. The earliest coating of rock at Earth's surface was a black rock called basalt. But when you heat basalt from below, if there's lots of water around, the basalt partially melts. And that melt has a composition that's very different from the basalt. It's richer in the elements silicon and aluminum, in sodium and potassium. And so this melt is buoyant and it rises to the surface and it forms a new kind of rock called granite. And those granites form our continents. You also select and concentrate many rare elements in some of those beautiful minerals like tourmaline and beryl. Those are the things that form with granite. So here we have stage 4 of Earth evolution, about 1,000 minerals. But Earth started to do something even more dramatic in terms of cycling its crust into the mantle, and that's called plate tectonics, where Earth's surface continents would come together and split apart, they'd break. Some of Earth's crust would subduct, would go deep into the mantle and further melt, and those melts rose to the surface as new kinds of volcanoes. You have new kinds of ore deposits, some very dramatic metal-rich deposits called massive sulfide deposits, and lots of minerals, but you'll notice they're not very colorful. I think only a specialist could love the sulfur salts, but nevertheless, there are a lot of them. There are hundreds of them, and they form. We also have mountain building, and when you build mountains, you have high-pressure, high-temperature regimes that come into play, and then we now have a new set of high-pressure, high-temperature minerals, metamorphic minerals that come to Earth's surface. By the way, part of the way we know that is, hear that rumbling sound? Well, that's doing seismology. And seismology means you have sound waves that are produced and they go deep into Earth and they bounce off different layers. And it allows us to understand the internal structure. It allows us to model plate tectonics. It allows us to understand mountain building in new ways. So thank goodness we have rumblings going on because otherwise we wouldn't know how Earth worked. So here we have about 3,500 mineral species that form through purely chemical and physical activities. But remember what I said, that we now have over 6,000 known mineral species? So how do we get there? And you've probably anticipated the answer. Remarkably, the answer is life. Excuse me, because life makes minerals. So we have several stages of mineral evolution relating to life. I have to show you something about minerals and the origin of life. That was one of my big research fields. And it's just fascinating. There are all these things that minerals can do to help jumpstart life on a planet. It can select and concentrate molecules on the surface. It can catalyze reactions. It can serve as a template to build larger and larger biological type molecules. And so minerals played a key role in the origin of life. But turnabout is fair play because then life played key roles in the origin of minerals. And this is one of the things we mean when we talk about the co-evolution of the geosphere and the biosphere. So stage 6 is a very early period of life in Earth's history where there were tiny microbes that were able to exploit the chemical energy of minerals. Minerals that come deep from the Earth are very electron rich. They're like little leads in a battery. And so if you can take a microbe, you say, here's your electron-rich mineral, here's the microbe, and here's the atmosphere. The electrons flow through the microbe. They power the microbe like little light bulbs. And these are called chemolithoautotrophs. That is, life forms that use the chemical energy of rocks, chemolitho, to make their food. And so these microbes are remarkable. They still exist on Earth today. There are all types of, they're incredibly tiny. You need an extremely powerful microscope just to see a single cell. But that was stage 6. But we don't think there were a lot of new minerals back then. It's just that microbes helped make the minerals that would form anyway, make them faster, and make them in different kinds of layered structures that had never occurred before. But the big event, the punctuation event in the history of mineral diversity, was the great oxygenation event about 2.5 billion years ago, when life learned to make oxygen by harvesting light. And this photosynthesis was a game changer. Now, if you can imagine, here's a plot showing the variation of oxygen. And just to look again, once again, we're going back 4 billion years, 3 billion years, 2 billion years. And in the early part of Earth's history, oxygen was very, very low. But in this point at 2.5 billion years, there was this sudden rise, the result of oxygenic photosynthesis, and then oxygen was at much higher levels. There was a second great rise about 550, 600 million years ago, and that brought us up to oxygen at the current levels. And it's that rise in oxygen that allows new minerals, vast numbers of new minerals, to form. So these thousands of new minerals used all kinds of elements that were sensitive to oxygen. Prominent amongst them are the first row transition elements, things like copper and nickel and cobalt and iron. There were also other redox-sensitive elements, things like uranium, tungsten, molybdenum, that formed lots of new minerals because they also were oxygen-sensitive. There also are elements that serve in a different chemical sense. They're the negatively charged elements called anions. And all the major elements of life, oxygen, nitrogen, carbon, phosphorus, and sulfur, were redox sensitive, but there are other elements as well, and thousands of minerals incorporate things like arsenic, selenium, and antimony on top of all this. So these are all the elements that led to remarkable colors. One of the first things we see is the oxidation of minerals and the formation of iron deposits, vast deposits of iron, because suddenly you're oxidizing and turning those dull black rocks into bright red rocks. So here's the Karijini National Park, and in Australia, the Tom Price mine, one of the largest iron mines in the world. These are all deposits from about 2.5 billion years ago that were formed when oxygen came into the atmosphere. And then the remarkably beautiful minerals. Here's a bunch of the iron minerals. Most iron minerals that we see on Earth today would not have formed before 2.5 billion years ago. But it's not just iron. Look at the beautiful minerals of nickel and copper. So here, copper minerals, those beautiful blue and green things like azurite and malachite, they're some of my favorite minerals when I go to a museum. None of these would have formed before the Great Oxidation Event. Uranium minerals, 90% of all the known uranium minerals could not have formed before the Great Oxidation Event. And most of those early uranium minerals were a dull black or a brown color, but these oranges and greens and yellows are very characteristic of the more oxidized uranium minerals. Nickel, 120 of the 195 nickel minerals could not have formed before the Great Oxidation Event. And so all these beautiful greens and aqua types minerals, just spectacular variation of mineralogy. I love cobalt minerals. They have this very distinctive rose color. In fact, rosolite is one of the most common of them, and there's some beautiful specimens here at the ROMS collection. So all in all, thousands of minerals formed for the very first time, and they tended to be these gorgeous, colorful minerals, the minerals we all love. This is part of Earth's mineral evolution. And remember, we're only about halfway through Earth's history, 2.5 billion years ago. Now there's a stage 8, and this is a period of about 1 billion years during which the oceans, which were very oxidized at the surface, but very reduced at the bottom. It took about 1 billion years for all the iron in the oceans to trickle out and the oceans got deeper and deeper, more oxygenated till the modern way that the oceans work. So that's stage 8. Stage 9 is a period when Earth, at times, through cycles, was covered with one extremely common mineral called ice. It became the most abundant. In fact, many other minerals were buried so deeply that you could almost say they went extinct. And then the ice melted, and then ice went extinct, and Earth became a hothouse Earth, and it cycled wildly between these periods when all of Earth was covered by ice and periods when there was no ice, even at the poles. Really dramatic shifts for some short period of time. And finally, we have stage 10. This is the modern biosphere on land, where we form clay minerals, we form all sorts of deposits associated with life. And you think about it, you make shells out of carbonate minerals, you make bones out of phosphate minerals, you make all kinds of interesting diatoms out of silica. But also coal measures produce hundreds of new minerals, especially when they catch on fire, because when coal burns, it's like the refining, and you make new smelter-type minerals. It's amazing. And also when cacti display, and there's a picture of hazenite. I have to tell you about hazenite. It is named after me. It is right now the only mineral that's known only to be formed biologically. There's no non-biological way to form it by microbes directly precipitating that mineral. And it turns out it's microbial poop. I have to say it forms at Mono Lake. It's the only place it's known as Mono Lake, California. And it forms when the phosphate levels get so high during the dry summer months that the microbes can no longer stand at the phosphate levels, and they have to eject the phosphate. They poop it out, and it makes these little crystals. And then every time it rains, all the hazenite in the world disappears, only to come back the next year, as one of my colleagues said, hazenite happens. Okay, and I have to tell you a story about, oh, I love this. So I love trilobites. There's some incredible trilobite specimens. You can look at them and you see their eyes. The trilobite looks back at you. What could be better than that, than a fossil that looks back at you? And each of these little tiny lenses, it turns out, is a single crystal of the mineral calcite. That's CaCO3, calcium carbonate. And it has a crystallographic axis that's looking straight out at you. So each of these single crystals is aligned. But there's a problem, because calcite is a terrible material with which to make a lens, because red light and blue light bend differently. So everything is out of focus. So that doesn't work very well, but life always finds a way through evolution, selecting things that work. And if you want to correct calcite with chromatic aberration, what you do is you add a little bit of magnesium. But you don't add it uniformly. The middle may have very little magnesium, and as you go outward radially in each of these tiny little crystals, the magnesium content increases. It's zoned, which exactly corrects for chromatic aberration. An astonishing example of something that life can do that would be incredibly hard for us to manufacture or machine on our own. And then I also have to raise this question of, are we in stage 11? The Anthropocene epoch, when humans are creating our own level of new minerals. And you think about it, we use building materials of all kinds. We have waste dumps. We have mines that have new minerals forming on mine walls and mine dumps in the mine drainage and the acid drainage from mines that have such dramatic mineralization, quite beautiful minerals, but also very harmful environmental effects. And of course, all kinds of new synthetic materials, thousands upon thousands, tens of thousands of new mineral-like compounds. We use them in our lasers, we use them in our magnets, we use them in our semiconductors. These are all materials that humans make that are very mineral-like and will persist for hundreds of millions of years, even after all of us are gone. Okay, so mineral evolution. This is a very nice just so story. It's very qualitative. It has a narrative arc to it. It's quite pleasing because you kept getting more and more interesting things happening. So we learned that minerals diversify over 4.5 billion years, that there's always a new sequence of mineral forming processes, that life plays an incredibly important role, and life has triggered thousands of Earth's most colorful minerals by the formation of oxygen. So that's really neat. It also, and this was a surprise to me when I first did this paper, it also has become a way of teaching and presenting mineralogy to the public. And I have to take you back, speaking of museums, when I was a child, the thing that turned me into a mineralogist was visiting the American Museum of Natural History in New York City. And when I was 10, 11, 12 years old, I'd go, and every month I'd spend a Saturday afternoon in the mineral collection. Other people would go to the dinosaurs or the dioramas. I went to the minerals. And they were arranged in these display cases in the old Morgan Hall of Gem and Minerals according to what's known as the Dana system. You had the native elements, then you had the halides and the sulfides and the sulfosalts, and you go systematically through it. And every mineral had a label, and the label gave the name of the mineral, it gave the chemical formula of the mineral, it gave the crystallographic system of the mineral, and it would give a location. Never a word about the age of the mineral, how it formed, what process was involved. It was just simply a group of chemical objects, and really beautiful, and I love them, and I fell in love with minerals, and I wanted to become a mineralogist. But imagine how I feel now when in 2021 I was invited to be the keynote at the opening of the new Hall of Gem and Minerals at the exact same museum, the same hall, the same specimens I viewed as a child, but now arranged by the mineral evolution paradigm. So this has become a way of presenting minerals. And now at the Paris Museum, at the Vienna Museum, at the new Tucson Museum of Gem and Minerals, the halls are arranged according to mineral evolution because it tells a story, it has a narrative arc, and it's very powerful. So this to me is very moving because museums played such an important role in my own life. But I will confess that at this stage, as mineral evolution was being presented to wider and wider scientific audiences, it was painfully clear that this is a very qualitative approach, and science has to be quantitative, it has to be predictive, it has to use numbers, it has to use data. And so we had to figure out a way of making mineral and the evolution of change through time something that was quantitative. So we introduced a field called mineral informatics. This is the informatic age, and minerals are incredibly information rich. And so every specimen is a time capsule. It's waiting to be open. And you think about the attributes of minerals. Well, we talked about composition and structure, but all the trace and minor elements, there are scores of trace and minor elements. There are hundreds of stable isotopes. There are all sorts of solid and fluid inclusions that give you hints of the history. There are structural things like exsolution and zoning, twinning, the size and shapes of crystals, and of course the ages, modes of formation, and many, many other attributes. And so we can build data resources. So working with my dear colleague and Kim's mentor, Bob Downs at the University of Arizona, we have built the RUF database. This is a mineral database that includes all known mineral species. You can search by chemistry. We've also, though, built an evolution option with 200,000 data on a mineral, a locality, and the age of that mineral. So we can now look and see how minerals have changed through time. We also rely fundamentally on Jolyon Ralph's great personal endeavor, which is now an international effort called MinDat. It's astonishing, over 400,000 localities with 1.6 million reported mineral locality pairs, 1.4 million photographs of minerals. It's an incredible resource used by 1 million people a day. We also, of course, have great literature, the Handbook of Mineralogy, rock-forming minerals, all kinds of published articles. These are the data sources that we use, and this allows us to ask some really big questions. So just quickly going through these, how has mineralogy changed through time? Can we predict localities of sources of critical mineral resources? How does Earth's mineralogy differ from that of other planets and moons? And how did the geosphere and the biosphere co-evolve? These are the kinds of questions we want to be able to answer quantitatively. And so we use various informatics approaches, and I just want to introduce briefly to you, because here we go from Earth's most colorful minerals to an incredibly colorful way of representing the distribution of minerals using data science. So I love these because these diagrams are literally beautiful. So first let's talk about the distribution through space and time of minerals. And this is distribution analysis. Here's a very simple diagram, a graph, but let me explain what you're seeing. Once again, we go back here 4 billion years ago, 3 billion, 2 billion, 1 billion, to modern times. On the vertical scale are bins 50 million years each wide, showing all the known localities, how many localities occurred during that age distribution. And this is a graph for all of that first row transition elements, things like copper and nickel and cobalt and iron, vanadium, those elements which are so important for economy and for biology as well. So what we see here, these are also colored by their oxidation states. And we see two really important, fascinating trends to tell us something about how minerals form. First, these red bars indicate periods of Earth history when all the continents came together in what's called a supercontinent. So these are interesting times where one side of Earth is a huge global ocean, the other side of Earth is just a mass of continents. And when continents come together, you have building mountains. Those mountains foster mineral formation, and the mountains also protect and preserve the minerals. So these times of supercontinent formation are also the maximum times of mineral formation. We see this over and over again. We also see this dramatic change in the average oxidation state of minerals. Copper comes in +1, that's the more reduced form when you don't have oxygen around, and then copper 2+ when you have more oxygen around. And you'll see the ratio of that green to blue is really quite dramatically increasing, especially in the last 500 million years. And we can do a skyline diagram where we plot all of these first row transition elements. Each one has its own distinctive character, but there are also commonalities. So you can spend a lifetime just studying what's represented on a graph like this. We've done this for the entire periodic table of the elements. You can go online with our data resources. You can click on your favorite element, like carbon, and you can see how those minerals have changed through Earth history. And we can play other tricks. Our dear colleagues at the University of Sydney have begun a project called the G-Plates Project. And this is actually trying to model how Earth's continents, as you go back in time, how have they changed? How have supercontinents formed and gone apart? This G-Plates platform now goes back 1.8 billion years. It's just remarkable endeavor. And what I'm going to show you now is just the last 350 million years, and the little dots that come up, each is a manganese mineral, where it formed and when it formed. The three colors represent three different oxidation states of manganese, and what you'll see is that almost every dot forms at or near a plate boundary. So this tells us how important plate tectonics is to understanding critical resources of our planet. This is just an amazing graph and is really opening up a whole new frontier in exploration mineralogy. Now, a second thing we do is actually predict locations of critical resources using what's called association analysis. And you all know what this is, even if you haven't ever actually used it, because if you go on Amazon to order a book or some other ordering facility, very commonly they will quickly come back, sometimes within a second, said, well, if you want this book, you're probably going to like these other things. Now, how in the world did they do that? Well, they have information, they have data from millions of people. People bought product A, and either they do like or they hate some other product, and they see all the correlations that are going on, and they can make a prediction for you. Minerals are exactly the same, because some minerals have very close friends that they love, and some minerals have other minerals that they hate, and they're never around. And so you can look for a mineral based on what other minerals are present. The first person to do this was Jan Ralph, the Mindat founder, and he said he loved the mineral wulfenite. He's a mineral collector, and he wanted more localities for wulfenite. And so he said, where can I go on Earth where wulfenite has not been reported, but we predict it's there? And he made a prediction that there's a New Mexico locality. He said, let's go here. He lives in London, so he sent some collector friends to go out here. They looked, and lo and behold, they found this specimen of wulfenite. So that was an amazing prediction. We've extended that, working with mining companies, to make specific predictions about uranium deposits worldwide. And here's critical resources, lithium and rare earth elements, which I'm sure you've all heard about. So each one of these icons shows one of our predictions. And every one that you see in red, people have gone out and discovered new deposits of those resources. I think that's absolutely remarkable. It's predictive mineralogy based on informatics approaches. And this has now become a major approach for every mining company. Every mining company now has data scientists in their employ. A third way of looking at minerals, and this is my favorite because they're so beautiful and they're so intriguing, is basically called network analysis. This is where you're looking at a graph that shows you how different minerals are linked. And you can think of this like a social network. You have your close circle of family and friends, and they have people that they know, and they have people that they know. And you can draw a network that links all the different kind of connections. You could have a same kind of network based on cell phone calls that you've made and other people have called. But in mineralogy, we just talk about which minerals are most closely associated with which other ones, and you can plot them out. We also have something on the right-hand side there, the chord diagram, that shows pairs of minerals and how often they occur together. Just beautiful diagrams. So this is how a network works. Here's a common rock. I mentioned granite before. And granite is made of associated minerals, minerals that are intimately connected to each other in a single rock. And you can say, what are all the common minerals in igneous rocks like granite and basalt? Let's make a network and draw connections between which minerals are close together. There's a granite, a typical granite. There's another kind of igneous rock called olivine basalt, and yet another one. In fact, all of the major kinds of igneous rocks are shown in this one graph, and much more information is in addition. What we call phase diagrams, which people spend many, many years trying to determine experimentally. You can actually extract them from a network like this. So we can look at all kinds of networks. This is a much more elaborate recent network we did of all the igneous minerals. And we colored it according to how closely each mineral is associated with another. And we find, we didn't constrain this in any way, but there are 4 major communities of igneous minerals. And this was quite a surprise because I thought there was a continuum across all the different kinds of rocks that we have. But no, that's not true. They're quite separate. This becomes an interactive diagram. It's all on our website. You can go and you can what we literally call play with this yourself. You can change the characteristics. And so these are interactives. I'm now changing the strength of connection, making it more and more demanding that 2 minerals have to occur 50% of the time or 75% of the time in order to be shown in a diagram. We can also, and this is now at 78%, so it's much more sparse. You see how distinctive these different clusters are, and we can put this back to a more consolidated form. Now we're at about 34%. We can type in a favorite mineral like bertrandite. We can click on it, and there's bertrandite. You can see what bertrandite's connected to, and then start studying that particular mineral. You can also change the attributes. In this case, we change it from something called centrality to abundance. So you notice there are 2 really big circles, fluorapatite and the other one, the green one there, is magnetite, and they're connected to almost everything, so they're very centrally located in the network and kind of keep everything pulled together. Really fascinating details. Here's another network that Shauna Morrison, my great colleague now at Rutgers University, did on 243 commonest copper-bearing minerals. And she colored this with 3 colors. You have the red colors are all the sulfides. That's where sulfur occurs, but there's no oxygen. You have the blue nodes where oxygen occurs, but there's no sulfur. Remember, these are all copper-bearing minerals. And then where sulfur and oxygen occur together, those are called sulfate minerals. And you see they're already strongly partitioned. And again, you can look at this. Chalcopyrite is the mineral in the center that's connected to everything else. Chalcopyrite is incredibly common. But other minerals are connected only to one small subset, the blue subset or the orange subset. And we can do this in 3 dimensions. This is my good colleague Dan Hummer, now at Southern Illinois University, and he colored all these nodes representing 400 different manganese minerals in 3 colors. Red is the most reduced, 2+ state. Yellow is 3+, blue is 4+, and you'll notice there are three sort of different clumps. That one up in the top, those represent manganese phosphate minerals in pegmatites. That's a group of reduced 2+ minerals. The group over there on the right-hand side, that's the high-pressure metamorphic manganese minerals. And the big clump in the middle, that's literally called a hairball in the network science. And the hairball contains all the things you find at the surface, includes a lot of gunky black stuff that you'd probably walk right by and never notice. So Dan did this in a three-dimensional network where you can also explore it. You can click on things, you can zoom in, you can zoom out, you can rotate it, and you can see in 3 dimensions this object. For those of you who are mathematically inclined, since there are 400 nodes, you're seeing a projection from 399-dimensional space. And that's because each of the nodes is connected or not connected to the other 399. So that's, and we can do this in virtual reality. So here's Shauna Morrison looking at a carbon mineral network. And you actually walk into the network, you can essentially touch nodes, you can find out what they are, you can see what they're connected to. It's a truly mind-blowing experience to experience one of these mineral networks in 3 dimensions as you're walking through it. Then finally, here's this core diagram. Oops, I'm somehow going the wrong way quickly. There we go. Okay, so this is a core diagram. These are the 30 most common cobalt-bearing minerals. And you can see every known pair of coexisting cobalt minerals. And there's all sorts of trends. If you're interested in critical element cobalt, which is very important in modern technology, there's a lot of details here that have never been revealed before because you here are looking at every single known pair of cobalt minerals on Earth. We can do clay diagrams. These are so colorful. I just think they're amazing. This 2-dimensional, that's odd. We're doing this is a 72 by 72 matrix, so there's over 5,000 matrix elements, and each one is colored according to whether those 2 chemical elements occur more commonly than you'd expect, just given crustal abundances. And there's a lot of interesting things. We're interested in cobalt and arsenic, and that's that hot spot down there, but there are many other details here. You could spend a lifetime studying this, and then we can do it in 3 dimensions. Here is a 3-dimension clay diagram, 30 by 30 by 30 for 3 different coexisting chemical elements and minerals, colored by whether they're more or less likely than you'd predict based on crustal abundances of those elements. And 27,000 different matrix elements, and you can animate this, you can go in, you can pull out individual slices, you can study all different ways that elements are distributed in Earth's minerals. Truly a revolutionary way of thinking about mineralogy. Okay, and finally I want to talk about what is, for me, sort of the grand culminating project of my career called an evolutionary system of mineralogy. A system of mineralogy is a term of art. Back in the 19th century, before they had a clear idea of how chemistry and structure affected minerals, virtually every mineralogist would publish a system of mineralogy. It would be a book, it would sit on a shelf, and there may be 100 competing systems. Then along comes James Dwight Dana's 3rd edition in 1850, which set aside all the previous ideas and said, here is a way of using chemistry and structure to define minerals. It's the system we still use today by the IMA. So for 170 years, there has been one system of mineralogy that's been accepted. That's the Dana system. What we proposed is we need a new system. Not to replace the old one, but to complement it. Because the old system, remember the IMA system, says you have an idealized chemical composition, an idealized structure. And if you think about it, that means you're using the minimum number of bits of information to distinguish a diamond from quartz, from calcite, from some other mineral. What we say is we should do something a different way. So in some cases, we take IMA species and we split them into multiple kinds. In some cases, we take several IMA species and lump them together into one kind. In some cases, we add things that aren't part of the IMA system because they're not crystals, but they're really important in geology. So this is our proposed system. So let me give you an example of something that we split. You all know what diamond is. It's pure carbon in the diamond crystal structure. That's what IMA tells us. But there are many different kinds of diamond. There's diamond that formed in the atmospheres of ancient stars many, many billion years before our solar system. In fact, we suggest that diamond was the very first crystal in the history of the cosmos. So that's stellar diamond, and they're tiny, tiny things that formed billions of years ago. Then we have type 1 diamonds, which is most familiar to. These are the high temperature, high pressure diamonds that you typically find in a diamond wedding band. They formed in a deep aqueous, a water-rich fluid that was saturated with carbon. But there also are diamonds out there that are type 2 diamonds. The big Cullinan diamond, most of the very large, fancy diamonds are type 2 diamonds, and they form deep in the mantle at high temperature and high pressure, but in a metallic fluid, and we can tell that because of the metal inclusions in these diamonds. And then there's impact diamonds, things that form, for example, when an asteroid hits a coal seam, and you form these diamonds through very high pressure shock experience. And then there's something called carbonata, which is this black mass of sintered diamonds, and nobody really knows where it came from or what it is, but it's really different. So we say there's at least 5 kinds of diamonds. They formed in different ways, they formed at different times in Earth history, and they have different physical and chemical properties, and therefore these are different kinds of diamonds. The world record, I love, there's an incredible collection of pyrite here at the museum. And I love pyrite because it's the most diverse known mineral. It forms in 21 different ways, sometimes at high temperature, sometimes at low temperature, sometimes with water as a fluid, sometimes with sulfur as the fluid. Sometimes it's abiotic, but other times biology, microbes can create pyrite deposits. So there's 21 different ways, and we think you should not say, well, we found pyrite on Mars. We should ask the question, well, what kind of pyrite is it? Because if it's high temperature, sulfur-rich fluids, then okay, that's interesting. That's sort of the way it happens in volcanoes on Earth. But if it's biogenic pyrite, you've made a discovery that will change the way we understand life. And then in some cases, we lump things. There are 37 or 38 approved species of the mineral tourmaline, and many of them are very beautiful, and they occur all over. But tourmaline has these very subtle compositional shifts. And if there's 51% magnesium and 49% iron, it's one species. And if it's 51% iron and 49% magnesium, it's another species. And a crystal like the one you see over there on the right-hand side, that crystal has 8 different tourmaline species all in one crystal. And we say, okay, that's great. I mean, you can catalog it that way, but we think it's one thing. It's tourmaline that formed in a particular environment with a particular chemical, right? It just happens to be zoned, as it were, with different regions slightly different and therefore representing different species. So we lump tourmalines into 2 different natural kinds. All those 37 species come down to 2 kinds. And then there's amorphous material, volcanic glass, obsidian, coal. That's a really important sort of amorphous, not well-defined material, but it tells a lot about Earth history. And things with names like limonite and pyrolusite. All of these were included in Dana's system, by the way, but when we started learning how to do crystal structures, they found out, well, these don't have very regular crystal structures, so they weren't included. But we think they're critically important. For example, on Mars, when we look at the sediments at Mars' surface, when Curiosity analyzes them, as much as 70% of the Martian surface is amorphous, that is non-crystalline materials. How in the world can you understand the history of Mars without understanding amorphous materials that make it up? Okay, so what we did, this is during COVID, I spent about 9 months kind of watching TV and going through every mineral reference and textbook. It took 9 months to go through 6,000. Well, back then it was about 5,700, and identified that there were 57 different modes of formation that I could identify. And so I made this table. This is a spreadsheet all done by hand, line by line, 5,700 lines, 57 columns, and each column would tell you whether or not that mineral formed by that paragenetic mode. And this then became the basis of a quantitative evolutionary system of mineralogy. This is being done with my colleague Shauna Morrison at Rutgers. 8 of these parts are now published. There'll be 12 in all. 9, 10, and 11 are in preparation right now. The final step, 12, that's the terrestrial biosphere. That's down the road, but I hope to finish it all in 3 to 4 years and then put it into a big book and have my own system of mineralogy. That'll be really fun, in the tradition of the 19th century, if anybody reads books anymore. And here's what we do. We say we have a mineral species, and typically it's the IMA name, like graphite, which is a form of carbon, or moissanite, which is silicon carbide, but it's a binomial nomenclature. So we say, what kind of graphite? Well, on the right you have supernova 2 graphite. Graphite formed in an exploding star. On the left you have AGB. AGB is a kind of star, an old star that has very energetic atmospheric release, and so you form minerals, so that's AGB moissanite. Now we can do this with my dear colleague Anirudh Prabhu, who's an information scientist, and help us build these network diagrams. This is a network that has 2 different kinds of nodes. So you have stellar nodes, and each of those star-shaped nodes represents a different kind of star, and each of the diamond-shaped nodes represents a different kind of mineral, and every mineral is connected to one or more kind of star, and every star is connected to one or more kind of minerals. And this is the complete visual representation of all the stardust, all the stellar mineralogy that we know. And then you start going through stages. So, solar nebula, this is this stage 1 that I talked about, the early condensates, and you start looking and seeing more and more minerals added to the list. And then here's even more interstellar clouds being added. And here's part 3, part 4, part 5, and we see the 300 minerals that are formed by primary processes, igneous processes, but also by alteration with water, alteration with heat, alteration by impacts. All those minerals still fall to Earth today in meteorites that are about 3.56 billion years old. Part 6 is our guess of what Earth's earliest mineralogy, actually before the moon even formed. And what you'll see is in red and yellow, those are all the meteorite minerals we had before. In green are new minerals that formed on Earth that wouldn't have formed as part of the meteorites, about 450 minerals in all. What you see there is the original stellar network that I showed you at the very beginning. It's got to be in there, it's just that everything's now surrounding and it builds out and out. And we think this is probably very similar to the network of minerals on the moon. But Earth has more. So here is part 7. These are all the igneous minerals and how they're associated. And then fast forwarding, here is this incredible network of 5,700 minerals, 57 different ways it forms, and then colored in subgroups. We have 11 subgroups here representing different things. The big green subgroup that's off to the right-hand side, you'll see that network is all the biological minerals. In red, there's some high-temperature minerals. You see all kinds of structures, and we've learned so much from this graph. This is a really amazing representation of all of Earth's mineralogy and how it formed, and we can also think about how it changed through time. And I just want to end by sharing with you some of the findings that I think are so extraordinary. First is the incredibly important role that water plays in mineral diversity. We think that 90% of all those 6,000 minerals, more than 5,000 minerals on Earth, formed as a result, directly or indirectly, of water-rock interactions. If you didn't have water interacting with other rocks, you simply couldn't have formed these minerals. And that's why dry worlds are so poor in mineral diversity. Another object is, and this is really fascinating to me, the incredibly important role of rare elements. So we have 41 elements that are essential to form one or more minerals. But collectively, those 41 elements are rare. If you picked up a handful of soil, only 1 in 10,000 atoms would be one of those 41 rare elements. And yet they account for 42% of all the minerals known on Earth. And I think this relates back to water-rock interactions, because it's only because water interacts with rocks that you select and concentrate those rare elements in precious pockets. A pocket of tellurium mineralization, a pocket of lithium mineralization, a pocket of rare earth element mineralization that wouldn't otherwise happen except for that water-rock interaction. So this really is a consequence. A third remarkable finding is that more than half of the minerals on Earth can form through biological activity, directly, like hazenite, or indirectly, like the formation of oxygen in the atmosphere. And fully 34% of all, that's more than a third of all the minerals on Earth, are only known to form directly or indirectly through biological processes. So biology plays this huge role. And finally, we speculate that the structure of this network graph, which is different from the structure of the graph for the moon or for Mars or other worlds that we know about, that this structure, in fact, is itself a biosignature. That what you're seeing in the distribution and diversity of Earth's minerals is a sure sign that Earth is a living planet. So this is the main conclusion, that over 4.5 billion years, mineralogy has advanced, has expanded, has diversified as a result of physical, chemical, and ultimately biological processes. And those biological processes especially have led to Earth's most colorful minerals. We've entered this new age of mineral informatics when the information-rich aspect of minerals is telling us the history of our planet, the history of life. And I want to end with one final thought. It has taken Earth hundreds of millions of years, billions of years, to create its mineral diversity, 6,000 minerals. And yet humans, in the last few centuries, in the last few decades, have created 100 times more mineral-like structures than Earth has been able to do in its whole 4.5 billion year history. That's the power of human change. By the same token, it took Earth hundreds of millions of years, billions of years, to sequester and bury vast amounts of carbon-rich materials. That includes coal and oil and natural gas. And yet humans, in the matter of a few centuries, of a few decades, are releasing all of that carbon back into the air. Humans have tremendous power and ability to change Earth. Now, Earth has always been a planet of change. It will continue to be a planet of change. It will continue to be a planet that has thousands of incredibly beautiful mineral specimens. But only if we are wise, only if we are thoughtful about how our planet works and how we interact with it, will we be around for a long time to enjoy those beautiful minerals in a place like the ROM. With that, I thank you very much. I'm told there might be time for a few questions if you have them. It's hard for me to see the audience with the lights, but I think there are people on the aisle that have microphones, and if you wouldn't mind asking your question into the mic, and I'll do my best to answer. So.
Yes, just a quick question. What impact can you see, plus or minus, climate change, fracking, and AI would have on mineralogy?
You know, I was shocked not long ago when I gave a lecture like this at the Colorado School of Mines. I thought the students and the faculty would be thrilled to learn that we use machine learning, association analysis, to discover new deposits. And the first question I had was by a young student who said, "Aren't you just accelerating the destruction of the planet?" And I have to say, it made me think in a very, very different way. So yes, we have the power to use these new tools for discovery. I think science has the power to have figure out some technological solutions as well. But we have to do it thoughtfully, and as you may have noticed, if you noticed the news recently, there are things happening in my country that would tend to make me more pessimistic about our ability to approach these things. So I wish I had a more upbeat answer, but I think that there are huge risks, and humans have the potential to do great destruction to the planet. We also have the potential to nurture our planet and see that future generations can enjoy a museum like this, and come to lectures and have that kind of discourse.
Hi there.
Hi.
I don't know much about this field. This has been very interesting. I'm curious, is there a big question in your field that we can't answer today that you think we will be able to answer at some point, and what is the thing that unlocks that?
To me, the biggest question is the origin of life. How did it happen? We know that the chemical environment of early Earth, the geochemistry, the mineralogy, the water and the rocks, the oceans, we know something about the chemistry of that. But the leap from that kind of really very simple and basic chemistry that we can study in a laboratory to actually creating a self-replicating chemical system that's alive is an extraordinary leap. And we are still a long way, and I would love to see progress made on that. I don't think it can be done without thinking about Earth as an incredibly complex system with chemical complexity, with all sorts of chemical gradients and thermal gradients and volcanoes erupting and wetting and drying cycles and all sorts of other complexities that are hard to build into an experiment. But without the complexities that Earth has shown us exist, I don't see how we can make much progress. So to me, the experimental challenges are mimicking experiments that are realistic to early Earth. That's a big challenge.
Hi, thank you very much. You mentioned earlier about the human's tremendous ability to change the environment, change the world. And I guess it's all out of exploitation, right? It's we do it to survive, to improve our lives. I guess the question would be, do you see any possibility of a more productive aspect of exploiting?
Any possibility of what?
Oh, more productive type of exploitation.
Yeah. As a preamble, I'll say, we think about clean energy technologies, we think about battery technologies and electric vehicles and so forth. If we were to convert all the vehicles on Earth to electric vehicles, we would need 10 times the amount of copper in all the known copper reserves in all the mines on Earth. That's a huge, huge challenge. There simply isn't enough. There's enough copper in Earth, but to extract it economically is almost impossible. So I think we need to keep looking at new materials and new processes. And I'm very optimistic. There's so many smart people, especially early career people who are just brilliant and who are at the University of Toronto right here. There's just incredible research that's being done. But I think you need to fund those people. I mean, I learned when I was visiting the university earlier today, the salaries of the graduate students and the postdocs. To live in Toronto on 25 or 30,000 Canadian dollars a year is difficult, and if you're a full-time student, this is a challenge. But still, we have all these eager students who are desperate to learn and desperate to contribute and make the world a better place. And I have to be optimistic, because what else can you do? That's what we need. We need to support the education systems and honor the people who dedicate their lives to solving these problems.
Where can we find dilithium crystals so we can power
Yes.
the Enterprise's warp drive?
Oh, well.
Not serious.
Vulcan, where's Vulcan? I wouldn't be surprised if there is something that's not totally different from that kind of intellectual leap, that there's some kind of material, there's some kind of technology that could make a huge difference. And I don't know what that is, but there's so many people one of the things that a lot of people are working on is synthetic chemistry using photosynthesis. So basically, you can manufacture fuel just from sunlight, like plants do. But if you could make something that was 20% efficient and use sunlight and convert it into chemical energy, and then that converts back into products that you can use to recycle. That's the kind of, because the sun is this incredible source of energy, and we're using only the tiniest fraction of it. So to me, that's one of the directions. I know there's chemical research going on in many places around the world to discover a process. It's that kind of advance that really could make a huge difference very, very quickly. But it's not going to happen unless we support the research efforts of many, many people and keep an open mind. If you know the story, the discovery of batteries and electric current came from initial study of frogs' legs by, Luigi Galvani. It's a great story, look it up sometime. But fundamental research takes you in directions that you didn't expect. You would never study frogs' legs or build batteries to make a better light bulb.
Hi, I was listening to a lecture some time ago. It was a Cambridge group who were looking for life on other planets. And the thing that struck me from their presentation was that it took them more years than they were willing to admit, that they'd started off as astronomers and then close cousins of physicists had joined. It took them more years than they wanted to admit before they thought, hey, maybe we should ask a biologist what life is and what we're looking for. And I'm noticing all sorts of crossovers in your work, and clearly data scientists and chemists and so forth have been cooperating with you. But I'm just interested in your collaborations, and particularly when it comes to the impact of biology on minerals. Have you had collaborations with people in that field too?
So I'll answer that in two ways, because this is a question that's near and dear to my heart. When I was early starting career, I was an expert in one tiny, tiny little field. Maybe 10 people would read my papers, but I was the world's expert in that tiny little field. And everybody I hired as a postdoctoral fellow to work with me, I trained to do exactly what I did. And about 25 years ago, I saw the light and realized that I knew what I was doing, and training more clones of myself was not necessarily making scientific progress. So at that point, I switched and said, all my postdocs are going to be people who do nothing like what I do. I hired people who are paleontologists or geologists or data scientists. People who really had different expertise in it, and that made a huge difference in my research. But even more important than that was when I had this opportunity to teach at George Mason University. That's the largest university in Virginia. It's a university that largely commuting. It's a very diverse community, about 50,000 students now. And I was brought in as a university professor. That is, I was not part of any department, and I was asked by the president to develop a course to teach undergraduates about science. Undergraduates who were never going to be scientists. And so suddenly I was teaching about physics and chemistry and biology and geology and astronomy and the scientific method and the history of science, and we would, every week we'd look at a great idea of science, but in the terms of, what is cancer and how it works? What are viruses and vaccines? What is a cell? What is a molecule? What's a chemical bond? The sort of most basic science things. And it made me step back from my specialty, which was so narrow, and say, wow, all these ideas, it's not like you have a separate physics and chemistry and geology. They're all the same. It's all nature. It's what they used to be called natural science or natural philosophy. But now it's been divided up into departments that do very sort of specialized things. And the chance to teach at a university level a course that had none of those labels made me see the world in a different way. And so the questions lead you where they lead you. And inevitably in nature, you can't isolate biology from chemistry, from geology, from astronomy, from physics. They're all one and the same. It's all part. And any of you who are early career scientists or thinking about going into academics, read as widely as you can. Read outside your own domain, because there are a lot of smart people in those other fields, and it's wonderful to collaborate with them. Thanks, that's a great question. I see a question here in the middle.
Canada has a really foul reputation when it comes to mining. And I'm understanding that these rare minerals or rare earths that we need aren't that rare. What makes it difficult is that to extract them is incredibly polluting. Is there any way we can get these rare earths without destroying everything around it?
You're absolutely right that rare earths never occur in high abundance. I mean, if you have a deposit that has half a weight % rare earth elements, you've got an incredibly valuable. So you have to mine huge volumes of rock and extract these minerals, and rare earth elements often occur with other minerals that might be pollutants, that might in some ways change the water supply system of your area. Of course, mining is also very, very intensive in terms of using water, in terms of using the land, in terms of destroying ecosystems. I don't see any way around that if we're going to say, well, we need our own supply of rare earth elements, so we just have to go to these places. What we can hope to do is find the most concentrated deposits, I suppose. But unless we wean ourselves from the electronics that all of us rely on a day-to-day basis, there's simply no other elements right now that can do what those rare earth elements do. So that's a challenge. It's a challenge for chemistry, it's a challenge for industry, and certainly for ecologists to work together and try to find solutions. But I'm not enough of an expert to say I'm optimistic that that's going to happen.
Hi there. I'm wondering, is there an example of a mineral species ever going extinct?
I love this question. And absolutely. And the thing about extinction, so mineral evolution is not the same as Darwinian evolution, because in Darwinian evolution you have what's called common descent, so each generation sort of takes on characteristics of the previous generation. In mineral evolution, minerals can go away, like hazenite can go completely extinct for the rainy season at Mono Lake, and then when it gets dry, hazenite comes back again over and over again. There's no mineral genome, so to speak, that gets passed. It's just that certain minerals become stable under certain conditions of pressure, temperature, composition, and then they'll form, and then if the situation changes. Now, on Earth, we know that if we look ahead billions of years, 3-4 billion years, the sun will start getting larger and larger and larger. It will expand. It'll ultimately become a red giant star. It will swallow Mercury. It will probably swallow Venus. Earth will, when you look at the sun, it will be like the sun is like this. It'll have a red surface, but it'll be so hot that the surface of Earth will be totally scorched, be hundreds of degrees Celsius. And so many minerals will go extinct at that point. At that point, there'll be no hydroxides, there'll be no clay minerals, and some other minerals will disappear. So that's billions of years in the future, but we can imagine many scenarios in which minerals go extinct and some in which they come back again after they've gone extinct. Yeah.
Hi, just over here. Quick question on the side, sir. So you mentioned about the co-locations of the mineral discoveries. Is that, and I didn't quite understand that part, is it somewhat implicating with the fact that the 41 elements tend to be clustered in some way? And I'm just wondering if that's because if you mentioned about water being the main driving
Yeah.
force. Is that what's causing it?
So one of the really astonishing things is the way these rare elements go into different environments. So some lithium, beryllium tend to go pretty much together. Uranium tends to go with vanadium, but many of the elements just have their own niches. And the thing that's so amazing about the way the Earth works, and also the way biology interacts, is you form these little pockets of chemical novelty. And they can be quite striking, and then this has to do with the way hot water selectively dissolves certain elements out of some rocks. If you're more acidic, you get one set of elements. If you're more alkaline, you get another set of elements. If you have a little bit of fluorine in the water, you get another whole set of elements. If you have sulfur in it, you can start concentrating gold into gold deposits. So all of these are kind of separate, idiosyncratic. You can see common themes, but it's just astonishing how complex it becomes. We have scientists here working at ROM in the University of Toronto on how all these trace and minor elements get concentrated. And you look at adjacent gold deposits or adjacent metal deposits, and you can have even though they're very close together physically, they can have completely different chemistries. So you can distinguish one from the other just by the trace elements in the minerals. This is a vastly complex planet, and we don't think that the moon or Mercury or even Mars is going to have anything like that kind of surface complexity.
And I think we have time for one more very quick question.
I hope it's quick. I was thinking about the network map of mineral evolution that you showed about the sort of fingerprint of Earth. And it got me thinking about other planets and moons in our solar system, some of which have oceans, subterranean oceans and things. Can we make that fingerprint for other bodies in our solar system? And what would it take?
We're already trying to do this. Part of it is predicting based on just understanding of the compositions of those worlds. So for example, one of the things I found fascinating is Saturn's moon Titan. And there, the lakes aren't water, but they're methane. And we start mentioning, well, if you have methane lakes and water is a rock, it forms ice mountains, it forms these solid, the volcanoes spew magma, which is water, and then it freezes on the surface. What other minerals would you see? There'd be organic minerals. And there's just wonderful set of articles. I've been involved in some of them, and other people are much more expert than I am, and proposing all sorts of neat minerals on Titan. And one of the funnest ones is that if you think about a methane lake, and you say, what's the analogy to like the Great Salt Lake when it evaporates, salt crystals form around the edge? And the answer is, on Titan, those evaporites would be acetylene. Now, I don't recommend lying on a beach on Titan, because rather than those nice cubic, beautiful salt crystals that you find at Great Salt Lake, acetylene are little sharp needles. So you'd be lying down on a bed of needles, but imagine that. I think they'd be lustrous and black, is what people say that acetylene needles look like, little shiny, tiny, sharp. So thank you so much. You can tell that I really love this field of mineralogy, and I'm so grateful for the chance to meet with you this evening and share some of these ideas. Thank you.